We're getting some good numbers coming in, and I'm not surprised with this topic today. So OMUG, the Modeling Users Group of Oregon, we tend to meet quarterly, and we've stayed on that schedule for some time now. But there on occasion, there are times to call special sessions, and this is one of them today. I'm trying to think, actually. I was trying to think, when was the last time we held a special session like this that interrupted the quarterly schedule that we kept? I can't remember. But anyways, as they arrive, as they're pertinent to the workflow around Oregon and MPOs and the DOT here, it's nice to bring this technical group together and do a check-in and get some, I guess, a broader exposure to some of the work that's happening in the region. So really appreciate everybody showing up today, and we're scheduled for the next hour or so. And with us, we have Dr. Waddell. He wears two hats, I guess, one of UrbanSim and another, he is a professor at UC Berkeley. Paul's been around the area for a while. He's very familiar with Portland and Oregon in general. And to introduce him, I'll pass off to Jeff Hood here in a minute, but I did want to kind of go through the agenda here real quick. So yes, the majority of this meeting is around UrbanSim and some calibration methods for the UrbanSim model. As probably many of you know on this call, UrbanSim was selected as Portland Metro's land use simulation model from the retiring Metroscope. So we're looking forward to working with Paul and getting an UrbanSim model up and running, and learning more about calibration methods today. After Paul and Jeff talk, I'm going to just quickly wrap up the meeting with some announcements and kind of go to the order. And like I said, this is scheduled for about an hour-long session today. So with that, welcome to the special session around UrbanSim. And Jeff Hood from Portland Metro, I will pass the baton to you.
Thanks, Kyle. So that was a great introduction. I'm Jeffrey Hood, a researcher and modeler here at Metro, and the lead land use modeler. And as Kyle said, we've begun a contract with UrbanSim and Paul to build a new land use simulation model for the Portland metropolitan area. And Paul has been, and UrbanSim have been doing land use modeling in Oregon for, I believe, over 20 years now. I think the first UrbanSim model was in Eugene back in like 2000 or something, a long time ago. So he's a lot of experience and local experience. And the UrbanSim platform's gone through a lot of iterations. What we call it at Metro, we're calling the UrbanSim Classic model, is a open source micro simulation based platform. And the new UrbanSim Cloud model has some new exciting calibration features that are based on differentiable programming methods that allow the model to be calibrated jointly and longitudinally for all of the parameters in the entire model system. At least that's my understanding from Paul's sales pitches that we've got so far. And it's a very, very exciting. And the purpose of this session today is to learn, both. I'm hoping to get kind of like a 50-50 lens on this topic, kind of half of the why and the generalist kind of planning perspective about why you would want to do this. And then the other 50% get really deep into the technical details of how this works from a practical perspective. And, you know, obviously Paul will do what Paul wants, since he's the one who knows all about it. But with that, I'm going to go ahead and turn it over to Paul. Thank you so much, Dr. Waddell.
All right, Jeff, thank you very much for the introduction. And it's great to be meeting with all of you. I feel a bit like it's a homecoming of sorts. I worked with the Tulumet program from its early days, and that was a very exciting kind of early launching period for the work that I've been doing on UrbanSim. Also great to see a lot of familiar faces in this group. Of course, Liming Wang worked with me at University of Washington, and I was so happy to work with him. I asked him to come down and work with me at Berkeley, and now he landed right in between in Portland. So good landing spot there. And Jeff and I go back to days at Berkeley as well. So without further ado, I'm going to jump in the interest of time so that I can fill as much of those two agendas that Jeff just charted out for us. Let's see what we can do. And I'm going to go fairly quickly through the presentation. I do have quite a bit of material here. That's my tendency. I tend to jam up a presentation with a little too much ambitious content. All right, the welcome unknown participant. Here we go. So I'll start with just a little bit of a warm up, talking about the case for land use modeling. A long time ago, back in the 1990s, when I was trying to start working on this topic and developing modeling methodologies. It was a bit of an uphill climb. There was a lot of resistance to doing it. Transportation planners and modelers were used to taking a fixed set of land use inputs and feeding them into their transport models and calling it good. Having a baseline forecast was sufficient in terms of the land use side of things. They might run various alternative transportation plans through the travel models, but they would leave the land use inputs the same. And often those were done with somewhat manual techniques, Delphi techniques, GIS kind of homegrown tools. Portland Metro was kind of an exception to have an economist on board, Sonny Condor, that developed Metroscope and maintained it over many years, and had a lot of really good insights and algorithms, I think, embedded in it. So anyway, I think, come a long way since the early days of skepticism about long-term induced demand. I think I would be preaching to the choir in this particular audience to try to have to sell you on analyzing the impact of highway projects on urban sprawl, or the impacts of transit projects on infill and redevelopment, and obviously the circular impact of that on transit ridership. So practice has come along. It's dragged its feet, I would say, over the years, but it has come along to embrace the need for more integrated land use and transportation planning and modeling. I like to try to boil down the kind of questions that local governments, metropolitan planning organizations mostly, but also we work with cities and other levels of government. The kind of questions they ask tend to circle around these four topics. The first one is how does urban development influence my demand for infrastructure? How does it shape my regional transportation plan, or water and sewer for that matter, or electrical infrastructure? The second one is about the induced demand question. How will that infrastructure further shape land use and urban development? And how does that transportation infrastructure interact with the land use regulations that are controlled at the local level? How do those two interact with each other to shape real estate markets and housing affordability? A chronic question that I think almost everywhere is concerned about these days. And finally, in today's environment, how can anyone not be paying attention to climate change and resilience? We're seeing the Florida landscape being decimated again by a hurricane just 2 weeks after the previous one. This is becoming quite chronic, and the need to plan for extreme weather events, flooding, wildfires in the West. Obviously, earthquakes are still very much an issue as well. So with all that background and context, the many years ago that I started working on UrbanSim, I put together a chart like this, trying to identify the idea that we want to represent individual agents using microsimulation as much as possible, representing the household side of the market and the business side of the market and real estate development side of the market, and the role that governments play through their land use regulations and through their transportation infrastructure and pricing policies and so forth. And some of you would have read perhaps Michael Wegener's work around long and slow patterns of change. I'd like to break that down into choices that households and businesses make. Some of them are very short term, within the day, scheduling, activity generation, the trip making activities that people engage in. And then there are the longer term choices that might span a year or more than a year. Residential choices, whether to rent or own, workplace vehicle ownership. Those are choices that you don't make every morning when you wake up and go to work. And those are really the wheelhouse that UrbanSim has focused on. Same thing for the business side. And similarly with developers, real estate development, when there's an opportunity in the market to create new development, it can take years to realize that in terms of actual buildings that get constructed and opened for occupancy. So the timescales of all this do matter, and they vary quite substantially. Just a refresher here, at its core, UrbanSim is a set of discrete choice models, primarily. The same kind of models that you're using in your mode choice and destination choice models in the transport side. So the mathematics will all be very familiar to you. And then we're aggregating up the choice patterns that we get from different market segments. Geographically, we work down generally to the census block level, but also take substantial amount of parcel data into account. So this is really just to kind of relate that we're on familiar ground here for transport modelers. And of course, the glue that connects land use and transportation is accessibility. So this is just a visual representation exposing some of the analytics, the network analytics that we use in UrbanSim that do network-based calculations, either using zone-to-zone skims or actual street networks, as is done here, and transit GTFS schedules to calculate accessibilities by walk plus transit, two different types of opportunities in this particular set of slides. 15 minutes on the left, 30 minutes on the right, walk plus transit to retail. So fast forward a little bit. And after having been working on land use models since the 1990s, late 1990s, we've certainly experienced a lot of the difficulties of model building. And I would say a kind of a harsh retrospective view would say that land use and transportation models generally take too long to develop at a level of usefulness that you can actually put into operational use for regional transportation plans and other projects. And once the models are built, they often still take too long to run and are really difficult to update. You get a new batch of data, that's a huge lift. Now you want to re-estimate the models and then recalibrate them and so forth. It's a lot of work. And all of this level of effort and the amount of time and commitment that it takes to do these, I'd say has generally inhibited the growth of adoption of these types of models. And I make a reference down at the bottom here to Doug Lee's Requiem for Large-Scale Urban Models in 1973, and a sequel that he wrote years later that had, he talked about the 7 deadly sins of large-scale urban models and why they were such a bad investment. The industry, the modeling industry really, I think, suffered for many years from his critiques. It was quite on point and difficult to overcome the skepticism, in addition to the actual time and effort and challenges of getting to a good model outcome. It sounds like a great sales pitch so far, doesn't it? tell you how hard all this is.
Hey, Paul,
And so
could you click
yeah.
that little button that says hide the little dialog box?
Oh, yeah. I thought that was only showing on mine. Thanks
No,
for,
I think it's here too.
whoops. So what that does, is take away my, my viewing. So what happened here? Let me go.
Oh, really?
See if I can go back. Okay, so I got it back. All right. So now you can actually see what I was referring to. All right. So to take a long view of this, going back to around the year 2000, we built, one of the first models was in Oregon at Lane Council of Governments. I would say it's actually the first model we actually took all the way through an implementation and calibrated, and then I wrote a paper in Journal of the American Planning Association that highlighted the Lane Council of Governments application. And you can see some of the other MPOs that we worked with over the next 15 years. But we were only basically able to complete 10 models over a 15-year period. It was a really slow process. And I'd say in the early days, it would take 3 years roughly to assemble the data for a mid-sized to a large metropolitan area, every county having its own data schemas and formats and quality of data. It was just basically a Herculean effort to pull these things together. And then you get to about 2016, and that's when the current version of the UrbanSim company was formed. And we switched to a cloud platform approach, and we started focusing a lot more on techniques to automate and facilitate the model development process, because it was not scalable. It was too slow. So I've already made the points on the top of this, so I'll focus on the ones at the bottom. We put a lot of effort in the last, in that 5-year period from 2016 to 21, automating data pipelines, acquiring national scale data sets to have them ready to go. A lot more effort on the software engineering side of things, making software more modular and reusable. And the use of templates for variables, templates for model components, templates for models, so that it would be quicker to build a new bespoke model for another region. So we get to about 2021, and I think we had addressed some of the major challenges that were previously the main bottlenecks, the heavy data development effort in particular. And I would say by 2021, we isolated calibration as the main remaining barrier to improving the facility with which we could develop a model. And I refer here to calibration as the dark side of modeling. That might stimulate some interesting discussion in our Q&A period. And I say modelers don't like to talk about it, but when you look at papers about models, they often don't go into too much detail about the calibration process. And it's a bit of the more the art than the science, I would say, in model development. It's typically pretty manual. It's time consuming. It often requires hand tuning, adding some constants for geographies where a model is over predicting or under predicting, and trying to have that absorb the spatial errors that you might be trying to make the model handle better. The problem with that approach, though, is first of all, it's generally cross-sectional. And second, the more you calibrate by adding these constants, the more you squeeze sensitivity out of the model system. And that's really why we build models, is we want them to be sensitive to changes in policy inputs and appropriately sensitive. So they need to be both accurate, but they also need to be sensitive. And if you overemphasize the calibration with constants, you're going to lose some of that sensitivity. So to get to the motivation for this talk and the work that it is describing, we've already talked about how difficult it is to build and calibrate these models, especially longitudinally, and how that limits the adoption and the sensitivity of the models. And looking over our shoulder at the emergence of artificial intelligence models, it was just, astounding to see how rapidly these models had advanced in their predictive capabilities. But I think many of us that come from a more statistical and econometric background have, sort of a skeptical view of artificial intelligence models like neural networks because they are so black box. It's really hard to understand what's going on inside of them. And for, all of us in the transportation planning and land use planning fields, we're having to support public policy and analysis and planning. And we have to be able to explain why, if you make this intervention or another intervention, it's likely to provide better or worse outcomes. And if we simply take a black box neural network approach to making those predictions, and we can't explain why this policy is working better than that policy in terms of predictions, it's not going to go very far. Okay, I'm getting announcements about participants coming and going. I don't know if everybody's hearing that. But,
yes, I'm sorry about that, Paul. It's I've turned
oh,
off the notifications,
okay.
but for some reason they're still happening.
Right.
Yeah.
So, to put a point on it, the objective of this work is to find a way to leverage the best parts of AI advances in terms of their predictive accuracy to help ease the problem of model calibration, while preserving the good parts of the statistical and econometric models, which are their explainability and their utility for counterfactual analysis. Like, if we do this, what would happen? If we do that, what would be the alternative outcomes? And so that's the riddle that we're trying to solve. It's not an inconsequential or small problem. So to reframe the question, how do we get UrbanSim, a small area model of urban growth that we typically estimate using cross-sectional sample data like your household travel survey, census data, and other data sources, to approximate longitudinally observed data on urban growth? And can we do it without dampening the model's behavioral sensitivities? That is, try to avoid using dummy variables for geographies, aka constants or k-factors. And can we learn some things about how AI models are trained in order to help us accomplish this? So a brief digression on AI models, but in particular, I'm going to focus on graph neural networks, or GNNs. And they're all around us. And you're hearing a lot over the last year, of course, about large language models, which are a different class of models, generative and more focused on generally text or sequences. But graph neural networks are a large class of models. And examples here include something like PinSage, a graph convolutional neural network for web scale recommender systems. Uber Eats is using graph learning to power its recommendation system. And the mapping systems that we use to navigate and to anticipate traffic, like in Google Maps, are using graph neural networks to make their predictions and make updates and reroute you when you're about to hit a major traffic jam coming up. So we're surrounded by these tools, and they're using this technology very, very effectively. It's producing good results. And in these contexts, we're not so worried about the fact that they're a black box. We're not asking the Google map to explain why you routed me on this route instead of that route. That's not part of our user expectations for that product. We're just happy that it's getting us, through the traffic in a reasonably efficient way. But now let's break this down a little bit more. There's another subset here of models that are in this space called recurrent neural networks. And this is where we start looking at sequences that unfold over time. So events that happen over, minutes or hours or days or months or years. And so we can think of them as recurrent processes that repeat themselves, updating their status over time. And this is where I want to start making the analogy to an urban model like UrbanSim. Because in UrbanSim, we are taking the state of the region in this particular case, we're showing it starting in 2016. The model is doing some operations to update the state of all the agents and their locations, new real estate development and so forth, to create a new region in 2017, updates transactions. And then the model is again updating that as its input and creating another year. And it's doing that over a period of years all the way out to your forecast horizon. And that's when you might be calculating a set of indicators, and somewhere in here handshaking with the travel model to pass data to the travel model and update travel patterns as a result. There's a strong analogy, parallel between what we're doing in UrbanSim over time and what these recurrent neural networks are doing. So our thinking was, we should look at how they're training these recurrent neural networks and see if we can't appropriate that to solve our calibration challenges. So to start digging into the technical details, this is the second half of what Jeff wanted me to do in today's talk, is get into the nuts and bolts a little bit more. This is an example of a neural network, and the process by which the parameters are trained in neural networks and many other AI models is through a technique called back-propagation. So back-propagation is the thing we're going to focus on for a minute here. Think of back-propagation as looking at this particular equation shown on this slide. There's a forward pass of it where you're taking the parameters and multiplying them by the values of variables, and then you're taking that's informing another set of downstream calculations and so forth, all the way out to the end result. The backward pass is the back-propagation step. And if you meet certain criteria for how the model is constructed, you can use exact gradients to back-propagate through the equations in this recurrent neural network kind of structure, and do a very efficient update using exact gradients of the initial parameter set, and then repeat the process. So this is maybe a little bit easier way to think about it. We're leveraging automatic differentiation. This is where the differentiable programming that Jeff made a reference to comes into play. As long as everything is differentiable, every single step of the model system is differentiable, you can back propagate through it using exact gradients. And those exact gradients are partial derivatives of the loss function with respect to each weight, right? So the weight here means parameter. So for each parameter, we're calculating the partial derivative of the loss function, which I'll talk more about, with respect to each and every one of the parameters in that entire model system. Not just one equation, but all the equations. Okay? So yeah, I'm kind of going at this from high level and low level back and forth to try to make sure I ground the ideas. So here we're starting with the assessment of the data on changes over time that I observed. And I'm asking, what should the parameters of the simulator have been to approximate that observed data on changes over time, right? It's different than the previous way of doing this, which was asking which parameter values were most likely to generate a cross-sectional data set. And that was typically one equation at a time. So what we're doing now is asking what parameters were most likely to generate a longitudinal process and the outcomes over, say, 10 years. All right, so that sets the context for this, and hopefully enough of a technical introduction to give you some grounding in it. So what we've done is basically reprogrammed UrbanSim to be a fully differentiable simulation system. And it allows us to rapidly train detailed urban simulation models over typically a 10-year period of time with much greater accuracy, much more quickly than we've ever been able to do before. And I'll try to prove it to you, showing some results as we go through. So again, just visually to try to process what's going on here, there's a forward mode. We simulate from, say, 2010, starting at every census block value, base year data set in 2010, simulate year by year to 2020 to generate a sequence of observed data. And then we compare the outcomes that we've predicted after 10 years of simulation to observed data in 2020, which we have in hand now, from employment data, from LEHD, from census data for the demographics, from parcel data, and so forth and so on. And then using this differentiable implementation, we can do back propagation to make an inference pass to update the parameter set and run this loop, say, 2,000 times to do a 10-year simulation, do the backwards inference, and do it again 2,000 times. All right, so that's what we're grappling with in this differentiable implementation using back-propagation techniques. So the key concepts are that UrbanSim is redefined and re-implemented as a differentiable program. We're using optimization to take advantage of automatic differentiation. It calculates exact gradients of the simulator with respect to model input parameters. And then we're learning the parameters of UrbanSim from longitudinal data using this approach. So it's got to meet two criteria. It's got to be differentiable. You got to be able to take the derivative of it, and it's got to be able to calculate a vector of partial derivatives. So the simplest mathematical example here would be a simple function like fx is equal to x cubed, and now we can take the derivative of that and get the resulting equation below. Now, when you extrapolate from that to an entire simulation model system, you're dealing with not just one simple equation with one right-hand side variable and parameter, but you're dealing with dozens and dozens of equations, each of which might have dozens of parameters, or at least a handful. That means there are lots of parameters that have to have partial derivatives calculated. So I may be repeating myself a little bit here, but trying to drive points home. You can think of the simulator as a function with many inputs and a single scalar output. And we're taking a gradient of the entire simulator, the partial derivative of the loss with respect to each input parameter. All right, a little bit more on this visual might help ground ideas. So we're taking base data into an UrbanSim model, predicting spatial dynamics over a 10-year period. We're taking observed spatial dynamics from census and other data sources, and we're comparing them. How different are they in 2020? Or how different are the changes between 2010 and 2020 that are predicted by the model versus what we observe as change from these observed data sources? And by doing that comparison, we can then construct a loss function. The loss function is the key here. We want to compare something like the mean squared error of the difference between predicted and observed change in households, in housing units, in employment by sector, in rents, in prices, and composite those together into a loss score. All right, so now we have a metric that gives us a way to evaluate how good is the fit over that 10-year period from a particular parameter drop. And now, because of back propagation, we can go through an optimization step that goes backwards with the exact gradients, does an update of the weights, and reruns that forward loop. And we do that, like I said, about 2,000 times. This is another example of one of the components in UrbanSim, the proforma calculations, and unfolding that into a computational graph that is fully differentiable. In terms of software, what we've done is create a differentiable UrbanSim code base and use automatic differentiation libraries, which then can compile just-in-time compilation, which adds a lot of computational advantages. Compile to CPU or GPU or TPU, tensor processing units or graphics processing units, which add a massive amount of parallelization capability and further computational advantages. So some of the things that this brings us are capabilities like multi-geographic level optimization. So we can create a loss function that's measuring the gaps at the county level, the municipality level, at the tract level, and can composite those into a loss score, which is great to have these multiple levels of fitting of the model system over a 10-year period. Most valuably, it allows us to jointly optimize all of the model components together and over time. That allows us to, for the first time, really incorporate into the calibration process all the linkages between the models, all the feedbacks. I think when you consider how models are typically calibrated one equation at a time, and then you tie them together, all the glue that ties them together embeds various assumptions and calculations and other things that really do influence the end results, but are really just assumptions made by the programmer or modeler or both that are not subject to any part of the calibration process. You have to sort of work around them. We can also enable things like sign constraints. We want our price parameters, for example, in a household location choice model to be negative. We can incorporate regularization, things, techniques used in machine learning routinely by default. There's a lot of creativity available in customizing the loss function. Essentially, you can decide what are the desirable properties in terms of predictive accuracy that are important, including potentially sensitivity outcomes, and then build those into the loss function. And then you can also potentially extend this to multi-region learning and transfer learning so that you're taking advantage of characteristics that are beyond the dynamics of the single region that you're focusing on. So a little bit of a view on how well this works. I'm going to show you some results from Edmonton, Canada. This was a 6-month project we did starting in mid-January of 2024 up through mid-July. This is looking at the levels of outcome variables at the census tract level after 10 years of simulation. So we modeled from 2006 to 2016 at a dissemination area level, which is roughly comparable to census block. And then we aggregated the results to census tract and compared the end result levels observed versus predicted. And you're seeing correlations here that are extremely high. And same for rents and prices. So we're seeing even on financial characteristics like these, which are notoriously challenging, we're getting good correlations at the tract level on the levels. Now you might say, well, that's cheating a little bit because the 2006 values might be a pretty good approximation of 2016. And so fair enough. We also look at the change calculations from 2006 to 16. And so here we're comparing the amount of movement in households, the amount of change in households in every tract observed versus predicted, and the same for housing units and for jobs. And the correlations are still remarkably high over that 10-year period. This is the same set of results for changes in rents and prices. We're routinely finding that the rent change prediction is our weakest link. We're looking more into it to see if there's anything in the data that might be contributing to it. But even for prices, to get a 0.85 correlation on the change in prices at a census tract is, I think, pretty remarkable. Now, some other side benefits that we've been exploring from this differentiable approach and the exact radius is includes this one. It includes the ability to calculate short-term market clearing. That is, if a lot of demand for households to locate are overloading certain really popular neighborhoods in Portland, what would you expect the market to do in terms of its dynamics? Prices are going to go up, rents are going to go up. And as the rents and prices go up, it's going to get relatively less attractive for the households that were wanting to go into those attractive neighborhoods because it's just getting too expensive at some point. And so by taking advantage of the utility function and the trade-offs in the coefficients between prices on the one hand, which again should be negative, and positive attributes, amenity values, which might include, attractions, amenities, density, employment opportunities, accessibility more generally, those might be all increasing the attractiveness for that location. But then if the price gets ratcheted up, it's going to help balance that demand downwards to the point that it can help clear the market. So again, we can take advantage of these differentiable implementations to facilitate this kind of short-term market clearing. I've already mentioned a little bit about computational performance. I've mentioned that we run like 2,000 10-year simulations. Those are typically running in about 40 minutes or less for a region the size of Portland. So it's computationally just mind-boggling. We've run test simulations for regions as big as Chicago that are now running in about 40 minutes compared to 8 hours for the previous generation of the model. For most regions, mid to large regions, we're seeing 10 to 20 minutes to complete a 30-year simulation. And we think there's further opportunities for acceleration beyond that. One of the other things that we're doing is looking at not just growth, but also stability and decline. Even in fast growing metro areas like Portland, you'll see pockets that are pretty stable and you'll see pockets that are in decline. And so we wanted to be able to better tease out the specifications of models and the parameters that help us disambiguate, if you will, between areas that are stable, increasing, rapidly increasing, slightly declining, or rapidly declining. And we're not all the way there yet, but we're starting to get there. And the results are starting to look pretty good on that front. The other thing that, as a modeler, I found to be eye-opening about this approach and really opening up some creativity is that we often can hypothesize some process, some behavior, but we may not have exactly the right data to estimate the parameters of that equation. But on the other hand, leaving it out leaves out an important behavioral component. An example of this would be housing demolition, where we might not have, well, I would give an exception to Portland. You probably have great data on housing demolition, but a lot of other places don't. Household move out might be a better example for Portland, because the census data that we can observe shows households after a move, not before a move. We don't ever get to see the neighborhood characteristics and the demographic characteristics of households in the neighborhood that they're leaving. And then we see them in a different location next year. You have to have panel data for that. And aside from the Puget Sound Travel panel survey that's no longer being maintained, there really isn't any data like that. But we can hypothesize an equation like a household move-out model or a housing demolition model, initialize its parameters to near zero, and calibrate it in the context of the rest of the equations. And we're finding that it is working quite well. It's a little underspecified. There's a little too much degree of freedom. And so we have a dampening capability for these equations that we don't have really good observational data for. But it's an interesting new capability that we have not had before. Using these libraries and techniques that I'm describing, it allows us to basically follow the calibration process as it's running, looking at the convergence of the loss function, the parameters as they're moving, how the gradients are changing as the iterations are progressing, and be able to monitor whether there's any risk of exploding gradients or such side effects that would result in an explosion of not a number or nans and a failure of the calibration. There's an entirely different application that we're finding for this differentiable modeling paradigm, and it's in the range of geometry, generative geometry. And we're starting to adapt it to be able to generate building massing like the one you see in this picture that follow architectural styles. This one is a podium tower building typology. And we can impose the constraints of what the footprint of the parcel is. We can impose setbacks, bulk requirements, which are how you get that podium tower configuration, site constraints, lot coverage constraints, dwelling unit per acre constraints, and have the algorithm optimize the massing on the site subject to all of those other constraints. And we're now extending this to the financial calculations. So you could ask, what is the highest and best use on the site subject to all of those constraints? So we're pretty excited about extending this differentiable paradigm into those things. So I'm going to wind this down and open it up for questions shortly. And in terms of what's next, where are we going with this? We definitely want to be able to add a fully independent test period, which we're now able to do in the Canadian context because of the time frames that their census is taken. We've been able to calibrate from 2006 to 16 and now have a full observation at 2021. So we can have a 5-year period that's fully outside of the calibration period to evaluate model performance in early test mode. We're a little behind that schedule in the US because of the census release schedule, and the fact that our last one was 2020. But we will be acquiring that data sooner or later to have it. We think there's a lot of opportunity to integrate additional target data and loss function components and make those more available to users and model builders to be able to construct models quickly and tune them and adapt them. And importantly, to be able to recalibrate a model when there's a fresh wave of data or a new insight on a model specification or a new model component added, you can quickly recalibrate the entire model system that way. So we think it's going to allow us, and users to quickly generate additional model applications and really scale up. We also think there's potential to extend the framework to travel modeling. We've done some test work on it, mandatory location choice models and mode choice models, and are seeing some pretty interesting results from that so far. So stay tuned on that front. We'll see how far we can push it. And then I'll close up with a set of points here that we are now bundling this functionality as a cloud service, the calibration service. So a modeler can edit a model specification, upload it, and recalibrate the model and look at all kinds of performance metrics from it. We're hoping to invite a broader collaboration with the research community. The OMUG group is a great opportunity for us to think about a broader collaboration within the state of Oregon, and we'd love to pursue that. We'd like to have a benchmark suite that comprehensively addresses longitudinal model performance, both on accuracy and sensitivity. So that's a good place for potential collaboration as more modelers come together and help us think broadly about robust and rigorous benchmarks that might elevate the level of our calibration process in the industry. And most of you won't know this reference to Opus, but I'll tell you what it is briefly. A long time ago, in 2005, Eric Miller invited everyone that was working on integrated land use transportation models to a workshop in Toronto. And Leming will remember this. We proposed that the open source UrbanSim platform be basically opened up as an open platform for urban simulation. That is, we would invite all the other modeling teams to collaborate on the same code base. And instead of having each of them recreate an entire modeling infrastructure and software, let's just have one shared open source code base. It was a great idea that nobody liked. So it didn't happen. We produced Opus. We had a version of the model system that we released, and we continued working with it, but there was no broader take-up. I guess there's still too many advantages or incentives for independent publication of separate code bases. So just a couple of visuals to wrap it up here. This is showing the user interface of the model validation component. I've already shown you some results from Edmonton, but this gives you a side-by-side map comparison of the data that's observed on the left and predicted on the right. So you can drill into the amount of detail you see in the dialog box, the values on left and right. And the charts that I was showing some screenshots of, those are dynamically generated. You can see a list of model versions on the left. Every time we run create a new model version and calibrate it, it automatically updates a set of graphics like this for that particular model version. And it's available for all the different core metrics. So I'll leave that at that. And then I'll close with one little bit of graphic from the early work on the Portland application. This is just showing, a preliminary simulation. Don't take the predicted values here seriously. We haven't gotten any sort of buy-in on these results. This is just really showing you what the application looks like, and the fact that it's pretty snappy visualization and comparison of data. So with that, I am done, and I'll open it up for questions and stop sharing.
Yeah, thank you, Dr. Waddell. Interesting topic, and visuals and theories to share with our group today for sure. Lots to think about here. I especially like this concept of loss scores, and it seems like maybe a new metric that we can use for our transport models. Let's open it up to questions. I see a few hands raised. Let's see, Li Ming, I guess you're in my upper left-hand corner. Why don't you take it away?
Okay, cool. Great, thanks. Thanks for the great presentation. This is very cool. I still remember the days when we tried many different methods of calibrating the model. Simulating alien, it's at least the one I remember the name, but not sure. Certainly none of those work well.
Absolutely.
So very good, very cool, and good job on that. Two questions. One, since you're moving the calibration to recurrent neural network, kind of one of the machine learning method, what's your thinking in terms of moving the underlying models, household location choice model, or that to a machine learning based approach, since now you have all the mechanics
Great
working?
question.
And my second one is for the calibration process. How do you determine which model, which parameters were subject to tuning, which one you want to kind of fixed?
Sorry, can you rephrase the second question? I'm not quite sure I understood what you were.
For the calibration, which model and parameters will be calibrated in the calibration process? Which one will not? How do you determine?
Okay, so all right, let me tackle that one first. So you'll remember, because you helped me a whole lot with the early calibration processes, that we did do a lot of experiments with different calibration methods, and they were very, very computationally difficult and challenging, and the runtimes were an inhibitor to it as well. At most, we could only calibrate a few parameters. And even when we got more advanced with some Bayesian calibration techniques, it was still limited to a small number of parameters just because of the computational expense. So the short answer to your second question is, we're calibrating every equation, every parameter, all of them.
Okay.
It can be hundreds simultaneously and over a 10-year period. So the computational performance is that much faster that we can run 10 years of simulation 2,000 times, efficiently updating the parameters, and have a very well converged parameter set with all of the parameters initialized at near zero to start. Wow. And it converges pretty robustly. So we're pretty excited about that. All right, I had your first one and I've forgotten it already. What was your first question?
Machine learning, since the current method is still heavily rely on choice model, machine learning method for the underlying model.
So this is a great question, very thought provoking, and I think I have been both very excited by the advance in machine learning and artificial intelligence methods, but also very skeptical about their potential use. And I referred to it in my lead-in to the presentation that about the specific mechanics of this, is that I want to make sure that the models are interpretable and explainable. And so if you drop in, I mean, we could probably generate an even better predicting model that's a pure neural network type model, and that might slightly outperform on the validation metrics that we're producing now, but we wouldn't be able to explain it. We wouldn't be able to have confidence that we know what's happening exactly when we say, all right, let's put a new transit station here and look at its impacts, or let's change the zoning there and look at its impacts. and we'd see a different outcome, but we'd have a hard time explaining it. And so what I like about this is it still has all the same specifications, discrete choice models. The parameters are interpreted exactly as they were before. You can look at the standard errors on any one of them. You can interpret the parameter value. So it all remains in the familiar territory of purely interpretable, at least to someone familiar with discrete choice models and econometrics. Now, a policymaker, that's a different story. It's still, explaining a utility function to them in maximum likelihood is no small matter. But having said that, I think there's here's sort of my pecking order of ways that I would consider introducing more machine learning. I think the biggest opportunity that we're looking at right now is in the data creation process for historical and base year data. We have to assemble so many different data sources, as you know very well, and often those don't align perfectly. They'll have missing data, they'll have outlier values, they'll have all kinds of data problems. And I think there's a tremendous scope of opportunity for us to use smarter imputation methods, harmonization methods, even generative methods to be able to generate a more robust and comprehensive historical database with which we can then train the model. I feel like that's something that's a good place to apply these techniques, because it can be as black box as you want. You don't have to explain why it predicted the imputation that it did, as long as you can ground truth it, because you will have other data that you can use to verify the validity of it. So that's the first place I would look. I think there's some other intermediate places.
Dr. Waddell, let me interrupt real quick.
We're running low on time.
Yeah, we're short on time here, and we've got a couple, like 3 more questions. No worries. I mean, we could. Okay. This is very interesting, and as you mentioned, thought-provoking for sure. I want to. I'll let you finish your thought here. We'll take one more question.
Let's proceed to the other questions. I think I've talked.
Okay. Let's. I'm gonna. Let's see. In the interest of time, I'm gonna let Joseph Oth ask his questions. There's 2 more in the crowd. You guys can put those in the chat box, and we'll make sure that those get addressed to Professor Waddell as well. And then we'll wrap up here in the next 3 minutes or so.
All right. Hi, my name's Joseph Oth with the City of Hillsborough. I'm more of a macro modeler. I'm a micro modeler, not a macro modeler. So hopefully this question makes sense, but Oregon has smart growth and other unique land use laws compared to other states. For example, Oregon doesn't have the level of induced demand as compared to other states due to our land use laws. I was just curious, how does this predictive model picks up these unique land use laws and how these laws affect the market of growth?
And we have 2 minutes. I think all I could do is take a yeah. So first of all, I mean, we don't borrow model parameters from anywhere else. We calibrate all of this locally. We collect all the data locally, and we make sure that we represent the local policy context very directly. There's going to be all kinds of really interesting wrinkles in the Portland Metro application, urban growth boundaries being no small part of it. And so, I think we have to just take some time to make sure that we listen carefully. We appreciate the nuances that are unique and different, and also anticipate what the questions are that are going to be germane in the local context. What kind of questions, policy questions, do people want to be asking? I'm guessing housing affordability is somewhere in there, and the unique implications of the land use regulatory scheme you have, and how that might impact the market. So I don't have a short answer to that one. That's a long and hard question, and it's probably going to take us a good bit of time to tease that out.
Thanks for that question, Joseph. And thank you, Dr. Waddell. Carol, do you want to present the wrap-up slides, and then we can we can move along here. So again, I think the numbers I saw online in our audience participation was somewhere close to 40 today. So lots of folks interested in this, and not necessarily just from Portland or just from Oregon. So a real good turnout, I think, by lots of folks outside of this region as well. So the reach of this topic is impressive. So back to OMUG administrative pieces here, and thanks again, Dr. Waddell, for taking the time out today to present at our spotlight presentation today. And as you suggest, towards the end of your slides there, I think as the development for the Portland Metro model happens and findings start to surface, we'll definitely invite you back and Jeff as well to kind of give us some updates along the way. Switching gears here to upcoming events of interest, not necessarily OMUG sponsored, but certainly of interest to OMUG participants. Here in 2025, in January is the annual TRB meeting. Just want to make some announcements for that. There's also in next spring, there will be a TRB conference on AI and data for transportation advancement. We made a note here of others. I'll put in the chat another conference that I believe the Zephyr Foundation is sponsoring in, I think it's the spring as well. But anyways, this conference essentially replaces the application, or as I understand it, the old TRB applications conference. So this one's happening in Minnesota, but look for that in 2025. There's some more information on it in the chat box. OMUG specific, looking ahead, the next couple of meetings here this late fall. We've got another month and a half or so left, but we'd like to bring forward this topic of performance measures and standards and mobility policies. I know there's been some interest in the regional mobility policy in the Portland metro area that Metro has worked with ODOT on. So bringing that to the group. And in January, we have TRB brown bag. So folks that go to TRB kind of come back and report on lessons learned and exciting innovations. Typically that happens at Portland State, and it's an in-person event. And then likely next winter or spring, we'll start to look at some vision eval applications. So again, OregonModels.org. Email suggestions for any topics that you might find interesting. And once again, I just want to extend a sincere thank you to Dr. Waddell for joining us, and for Jeff Hood for kind of bringing this to light for us. And we're really happy to have sponsored this event today. So thank you, everybody.
Thank you. Thanks, Kyle. Thanks, Paul. Great stuff.
Thank you all. Bye-bye.